afternoon. Nice to see you. Welcome to the first Livino Data Science Seminar of the new year. So we've got a really good seminar today. And the person lecturing is Dr. Andrea Santamaria Garcia, who's a lecturer in artificial intelligence for particle accelerators at the Uni of Liverpool. So she spent her early years working on particle accelerators at CERN, after which she moved to, I think, KAT, Institute of Technology. There she created and led the AI for Accelerators team and co-founded the Reinforcement Learning for Autonomous Accelerators collaboration. She's recently moved to the University of Liverpool, where she's continuing her work on AI and accelerators. So, sounds great, and please go ahead.
Thank you so much for the introduction. I think I need to share my screen.
Yeah.
Just do the whole screen.
I'll double check what we see online. Yep. Awesome.
Can you see everything online?
Yeah.
Can you hear me? Great. So I hope I don't take too long, but thank you all for coming, and thank you also for coming in person. I'm going to talk today about machine learning for tuning and control in particle accelerators. So I don't know what's my public today, so I don't know. I expect physicists, but I don't know how many people are in machine learning. Machine learning is quite big, so I'm just going to focus on specifically tuning and control. So this is just little outline so that you know what's going to happen. You can see there's a huge bias towards reinforcement learning being the section with most slides, because that's what I like to do. But I'm going to be talking also about Bayesian optimization, which are two of the learning methods that are quite popular right now in particle accelerators. Okay, so for those who don't know particle accelerators, I'm just going to give a very brief roadmap introduction. So if you're in at least particle physics, you know that we have the energy frontier and that we're trying to increase our ability to generate new particles via high energy collisions. Of course, the most known accelerators is the Large Hadron Collider, which thanks to which we could discover the Higgs boson in 2012, and you have seen how we discovered particles very quickly early on, and how now it's becoming more and more increasingly difficult. So there are new projects like high luminosity LHC or even the Future Circular Collider that might help us in this frontier. But there's also photon science. We also have light sources that are used as microscopes, where we can probe from material to living systems to chemical reactions in real time. For that, it requires a very specific type of light with different, let's say, frequencies, intensities, and repetition rates. So we're also aiming to increase the peak brilliance, which is translates to the ability to probe atomic structures. That means we're going to the direction of fourth generation light sources that we call our free electron lasers. And in order to achieve all of these very nice goals that particle accelerator physicists have, we need technological innovation. There's no other way. We needed to keep up with these upcoming challenges, and technological innovation can come in terms of engineering technology, like doing new magnets, developing new materials, but also we consider that machine learning can be one of these technologies that might help us. So what are the, let's say, trends and challenges of frontier accelerators? So both frontiers, energy frontier and the photon science frontier, they both need denser beams for higher luminosity and brilliance, both of them. This means that we're going to have more particles in a reduced area. So we're going to have more complex beam dynamics, because particles, they have the same charge, so they repel each other. And that's going to lead to more complex accelerator design and operation. We are also aiming at larger circular colliders for higher energies. That means orders of magnitude more signals. So you can see here in scale how the FCC would look near the LHC. So suddenly we're going to have to process much more of information. And we're going to also be reaching machine protection limits, at least in the Hadron case for sure. And then there's also compact plasma accelerators with higher gradients that have very tight tolerances, and high quality beams are required, which are a perfect test bench for methods like Bayesian optimization, for example. So how does machine learning fit in all of this, in like this new vision that we have for particle accelerators? Well, on the one hand, we're looking at autonomous operation. So we'd like to have faster startups, faster commissioning, faster setup of special modes. Also continuous beam delivery. So we have a budget per year, and the more physics we are in, the better for us. So what's good, it's like failure and interval prediction, preventative maintenance, and virtual diagnostics. So we have the least amount of interruptions in our beam time as possible. We, of course, would like our accelerators to be energy responsible with increased sustainability, but also power quality improvement. This can be done with monitoring of our signals and energy load management that can be done, for example, with things like reinforcement learning. And this is more for the beam dynamics type of people. Intelligent control beam dynamics, that would be great. Complete phase space manipulation would be a dream. Tailored beams for users or instability control, which is something that at this point we can do with classical controllers, but as you know, that's quite basic. So we could be looking at more developed controllers than that. So what is tuning and control? Let's just make a distinction right there. Tuning and control, they are sometimes conflated, but they're fundamentally different. So in accelerators, tuning is just the adjustment of system parameters across repeated runs to optimize performance metrics. So operator level optimization. It's performed across iterations, not continuously. So we set up a beam, we have a run, and then we restart again. The parameters are typically static during the run, so we are not expecting our environment or initial conditions to change that much during that run. Historically, it's done by human operators, and it's limited to a few knobs at a time because that's what a human can do. We first change something else, then we change something else, and then we slowly adjust with our experience to the problem. And the feedback is usually slow. It's not something a human operator is not acting real time. Sometimes they do, but it's supposed to be a one-off thing. Examples, of course, are beam setup or commissioning efforts in particle accelerators. Then we have control, which is the real-time adjustment of inputs in response to an evolving system state to maintain and optimize the behavior. So this is real-time decision-making. It operates within the run. The actions depend on the current system state, requires low latency usually, and must handle delays and disturbances too. And stability and safety constraints dominate. And this is where we're looking at feedback systems in accelerators or control loops. Or most used feedback system is the bunch-by-bunch feedback system. It can be very complex or very simple. You can have transverse dampers for transverse damping to cavities that will do your longitudinal damping. You can also have low-level RF. So I know that this is very niche. So for accelerator physicists, if you're not an accelerator physicist, you need to know what it is. That's control. And now we come to classical control and learning-based methods, because I guess when we bring these new methods to senior accelerator physicists, they would tell you, well, we have classical controllers, they work very well, so what's new? What are we bringing? So there's a spectrum, right? There's the operational usability of models for real-time control. When models are accurate and usable online, which is what we usually use, proportional, integral, derivative, PIDs, things like that, then we can use that, and that's perfectly fine. There's some moment that we have models that are accurate, but partially observable or slow. Say you have a perfect simulation numerical solver of a partial, you have a partial derivative equation that you can solve exactly, but it's extremely slow. You cannot use it online. So that makes it unusable online, right? You can do it in simulation when you have a lot of computational power sitting in your office, but you cannot use it. So in that case, or when models are inaccurate or unavailable, that's where machine learning-based methods, learning methods can help us, right? So coming back to our classical controllers, they are highly effective when accurate models exist. They're extremely reliable for well-characterized regimes. So usually all of these feedback loops, we have characterized the regime and we have developed a very specific device that works well in that regime. And there's low operational risk, of course, otherwise we wouldn't put it in our accelerators. And there's strong interpretability. We understand this simple model. For learning-based methods, this is really useful when system models are incomplete or hard to derive, or it's just we don't have anything about that. It's also very interesting when dynamics change across operating regimes, so it's not a very fixed, characterized regime, it's just something very fluid. And when objectives go beyond stability, we just don't want to just stabilize this at any cost. There's performance trade-offs, there's multi-objective optimization to be taken into account. And where adaptation matters more than guarantees. So They are both not exclusionary. You should use both, in fact, but one should know when each one should be used. So as feedback becomes richer and more delayed, learning-based methods can exploit information that is actually difficult to encode in classical designs. Now, sequential decision-making. So in accelerator physics right now, we are dealing with two abstractions that are quite popular, which is Bayesian optimization and reinforcement learning. So what we need to understand before we get into the examples is what question are we asking and what information is retained versus discarded when making decisions, in order to know when to apply one or the other. So when we're asking what parameters maximize a performance or a metric function, that's Bayesian optimization, which is sequential decision-making over a static objective, meaning that your environment is not going to change dynamically, or you're not expecting it to. So the decisions of this algorithm, like they select what we should evaluate next. It assumes that the system can be represented as a static input and output map. We will see a little bit more about that. And it retains information only at that level of input-outcome pairs. Temporal structure is absolutely discarded. Is not really considered. It's an index, but not a state. So you have input, you apply to the system, you read your outcome, and that's how your information is used. But when we're asking what action should I take now, given the current state of my system, that's when reinforcement learning can come in. That's the sequential decision making, but over an evolving system state. Decisions select the actions given the current state. It assumes the system evolves over time under action. Information includes state, transitions, actions influence future system behavior, and time is actually part of the problem. It's structured like that. So this is actually how information is encoded, which is called a trajectory. In Markov decision processes, we have our current state that we observe however we can. Then our algorithm will take an action, will collect a reward that we have designed ourselves, and then it will observe the next state. So our information is more, it's more fine-tuned to the, let's say, time transitions of a dynamic evolving system. So you can see already that, of course, Bayesian optimization is more, it's better for tuning, and reinforcement learning is better for control. So when to use Bayesian optimization? So it's when the tuning problem could still be treated as a static optimization problem and the data collection is costly. So if you can think of, like, for example, clinical trials where you have patients and you are trying to see if a dose of a medication is working or not, that experiment is extremely costly because we're talking about living human beings and a very long time. So next trial you do, you want to be really sure that you're going into the right direction. Also for product formulation and design, it can be extremely costly to manufacture a demo, like a sample of your product. So you want to know that each iteration of that product, you are changing the parameters in order to maximize something. And of course, general parameter tuning and calibration. And this applies, for example, to experiments in a particle accelerator. We could consider that making experiments in an accelerator is costly. So tuning with Bayesian optimization would be a great tool for that. So Bayesian optimization, you need to consider that each experimental run can be treated as independent, as we were saying before. The control parameters do not meaningfully alter the future system dynamics. So meaning if you took some actions at one run, that should not affect technically the next run. Otherwise, your model is going to struggle. And the evaluation, if the evaluations are expensive, then and sample efficiency dominates, then Bayesian optimization, great choice. Of course, limited when, you guessed it, anything where actions influence system behavior, performance depends on temporal structure, we have delayed effects, and non-stationarity. What is reinforcement learning? When ignoring that temporal structure throws away relevant information, and this is very particular of reinforcement learning, when learning induced suboptimal behavior is tolerable within a safety envelope. What this means is that reinforcement learning needs to explore. It needs an exploratory behavior, either in simulation or in the real machine. And if you cannot accommodate, so usually we do the exploration in simulation, which is safe. But if you're going to deploy this system in a real place, like, for example, autonomous driving, you're not trying things, you're not exploring while the car is going. You do it in simulation before, and then you have safety envelopes for that. So reinforcement learning is very much applied to games, robotics. You have seen those robots learning how to walk where they fall and then they come back up again. So you need to be able to tolerate that suboptimal behavior in order for the learning to happen. So reinforcement learning with the control actions affect future system behavior. System performance depends on trajectories, not single outcomes. The relevant information is contained in system transitions over time, and adaptation to non-stationarity or disturbances is required. And we're acting in real time or not real time. So we shouldn't do this when the interaction with the environment is very costly. Actually, you're going to need quite a few interactions with the environment, either in simulation or during the experiment. If this is costly both in simulation and both in the real world, you're not going to be able to train this algorithm. Exploration should be accepted, otherwise it's not a good idea to use this algorithm. And the safety or stability guarantees must hold regardless of what your algorithm does. So now we start with Bayesian optimization. Are you guys familiar with it? Yes. So some of you will know this. I'm going very, very fast, but just a little theoretical introduction. BO is a sequential algorithm, as we discussed. It's for global optimization of an unknown function. And what it does, it just finds the maximum of that unknown function with a certain amount of observation. So for example, if a real function we want to find is this black line, and here's our maximum, what this algorithm is going to do is going to take some samples that are going to be guided, and it's going to figure out where the maximum is without having the full model of the function. We do not need to know exactly all of the values and peaks. We just want to know the global maximum. This is very important. And this is nice because it doesn't get stuck in local minimum as gradient descent might do. So this is great for a certain amount of problems. So we want to find the maximum of this unknown function with the minimum amount of samples of observations because they're expensive. Then Gaussian processes. So Bayesian optimization uses a probabilistic model or surrogate model, and it updates it sequentially as new data is gathered. So all of that data is going to go into a probabilistic model. It's Gaussian processes is the usual probabilistic model that's used, and it's modeled with a joint distribution of all of these observed function values. So we have our GP model, which is, of course, characterized by a mean and, here in this case, a covariance for a kernel. And this is like it's a probabilistic distribution of an infinite number of independent variables. And we can just sample from it. We can sample our Gaussian functions from it. The kernel is the core modeling assumption. There's many kernels, and it's just how the function relates to the inputs and the outputs that we were talking about before. So how they map together. We're going to map them through our kernel. So given a certain amount of observation, this GP defines the covariance matrix, and it goes quadratically with the number of observations. So at some point, if you have your Bayesian optimization model running, it's going to become too large because there's going to be, in order to calculate your posterior, there's going to be some inverses which we don't directly compute, but it's going to be still computationally expensive. So the larger your covariance matrix is, the more slower your algorithm is going to go. So it's a good idea to remove your old data and keep your model size constant. And for example, one of these kernels can be the radial basis function, which is one of the most commonly used. We have hyperparameters. These are parameters that need to be tuned. I don't go into that because we don't have time today. But we will need to tune that in order to adapt to our observations. So those are some of the main elements of PO. And now, how do we do this? How does it work? So I'm going to try to compress like a lot of information in one slide. I'm really sorry, but this is just an overview. So first you can choose your model, you choose your kernel family, you choose your initial hyperparameters and your noise variance, which can be unstructured, it can be 0, whatever you want. This defines what we call a hypothesis, all of your initial assumptions, your kernel, hyperparameters, noise variance. And the kernel will induce a prior, which is your first model, how your first model looks over this unknown function that you have. And it can look like this. We don't know what's going on, so we have a 0 mean, we have a certain amount of sigma. There's absolutely nothing there. Then we collect observations. We're going to be observing our function, and there's going to be noise. There's always noise that we call the evidence, which is going to be these pairs of inputs and outputs. And then with that, we can start building our little covariance matrix with our observations and the noise variance. And then we can compute a likelihood from that. I'm not going into what this means. We don't have time for that today. But unfortunately, these probabilities that we can compute, they are not over all of the hypotheses we have. We can only do it on one hypothesis with a certain set of hyperparameters. So we cannot directly apply Bayes' theorem, because these kind of relationships are only true for all distributions over all of the hypotheses. So in practice, we don't represent these exact probabilities, but we use empirical bias. So in practice, what a lot of us do is we just tune our hyperparameters to maximize this marginal likelihood, so the prior is consistent with the observed data. Long story short, this is done by an algorithm. You don't have to do anything. Once you collect some of the data, you're going to have a model that's going to be fitting your unknown function. And with that, you have, what's nice about this is that you get a surrogate model out of it, right? So you can use it to study your system further later on once you have built it with your data, which is very nice. So you can sample functions from your now GP function that has your posterior information. How does this look like in real life? We just collect data, and you can see the uncertainty. It's reduced in your model until you have actually a pretty good model of it, and you have a pretty good idea of what this very complex function looks like with a minimal amount of interactions with the system or observations. And I will not get into how this is done, because we don't have with the acquisition function. So examples. In accelerator physics, we usually have to use a series of rings because we need to progressively augment the energy of our beam. So we usually start with smaller rings, and then we inject into bigger rings. So injection is a process that happens in, basically almost all of the accelerators that are rings. And it's a process that has to be, many times it's done manually by operators, and you have to adjust settings of your injection chain parameters that you can see here. Like, we usually have a set of kickers. These are magnets, kicker magnets, up to magnets. They have different characteristics, but we all need them to activate at the time of injection. And they have timing and strength. They need to be properly timed. They have a ramp up and ramp down. And we also have our frequency system. So we wanted to automatically tune all of this system in order to have automatic injection with the best injection efficiency possible. And when we wanted to do that, it's because it's time consuming usually, and it can be easily stuck in local optima. So it really fits to global optimization and fast tuning. So we took all of these 9 tuning parameters and we applied Bayesian optimization. I don't get too much into how we did it, but you can see this is only with a few of the parameters. But what's nice is that they can be changed simultaneously, which is something that a human operator cannot do. And you can see that with time, our objective, even if it's noisy, it does improve with time. And we cut the injection tuning time by half by using Bayesian optimization. So that was quite a nice result. And you can see here that we have different injections. So this is the beam current. So here we damped and then we injected again. And we can see that the injection rate keeps getting better and better because our model is trained. So we get more and more observations, our surrogate grows, and the environment has not changed. So this is applicable because this has not changed that much. Then we did export this to the European XFL in DESI. This is my former PhD student, Chandran, and this was a very interesting result because we optimized one of the light coming out of European XFL, and we compared it to the simplex algorithm, which is one of the basic optimization ones. I was quite disappointed to see that we reached the same pulse energy, but one needs to look at the detail, because even if we reach let's say, the same output, you can see that simplex took many more steps, and it was a little bit all over the place. And usually when we change actuators, magnet settings, something like that, we don't want those values to be all over the place. We do like a progressive one because that can affect the hardware in a way that we don't want to. So we like much better the smooth path of the Bayesian optimization. And as mentioned before, you get a surrogate out of it, which can tell you, for example, like we tune magnets, so you can see how the sensitivity of one magnet with respect to each other, with respect to our objective. So, for example, we can see that this one is very tricky because this is the the optimal place when it can go, but here we have, let's say, much more leeway to go up and down. So this is very nice to see. So in summary, Bayesian optimization for us, it's very nice for expensive black box objectives, which can be any tuning problem in an accelerator. It's uncertainty aware by default because we have a probabilistic model, and it gives us a surrogate, which is very nice. It naturally interfaces for prior knowledge. This is a research that I have not shown, but we have a lot of people now trying informed priors in Bayesian optimization algorithms, which is very nice, which means that it doesn't start from zero. It already starts from a very nice starting point. It's very strong sample efficient and requires the static mapping that I talked about. And now I want to talk about optimization with reinforcement learning, which is not control, but it's optimization, because now you will see what I mean. We can also use reinforcement learning as a learned optimizer. So for example, you can train your reinforcement learning algorithm by interacting with a simulated environment in the control way, but then we deploy that algorithm as a fast optimizer for a tuning task. So this is just inference. It's just a mapping from observation to action, so there's no real control. We just have trained it that way, but at the time of deployment, it's a little bit the same as Bayesian optimization. So this sequential structure is exploited during training, but not in deployment, which is just fast inference. So again, this algorithm is not acting as a control, it's just as a learned optimizer. It's just learned it in a reinforcement learning kind of way. And this has a lot of advantages. Like, for example, we find faster convergence than BO at deployment, which is very nice. And it's also robust to slow and fast environment changes, which is something that BO cannot deal with because it has been building its surrogate with previous samples from another environment. And if the environment changes, you have to throw away all of those samples and build your model again, which is quite costly. The reinforcement learning-based optimizer doesn't have to do that. And it has constant time inference to the contrary of BO, depending on how you deal with the data of your surrogate. But it has some disadvantages, of course. Like it requires many interactions with the environment. So you better train it in a fast simulation. If you have a very slow simulation, that's not going to work. You need a careful problem formulation, so it's quite difficult to formulate these reinforcement learning problems. And generally, it requires much more engineering effort. So I guess the question is, do we really want to put all of this upfront engineering for this or not? So it depends on the particular case. And I'm going to show you what we did. So we did try a tuning task in an accelerator, trying Bayesian optimization and reinforcement learning as tuners, not as control. So we went to the RS linear accelerator at DESY, and we tried this very simple tuning problem, which is where you're saying these quadruples and these correctors to steer and focus a beam. So steering means we want the beam in a certain position on a screen, and focusing means we want the beam to be of a particular size on the screen. So our actions are the quadruple magnet strengths and stereomagnet deflecting angles. Our observations are the beam parameters on the screen and the magnet settings, and the goals are position and size on the screen. We tried this both in simulation and in the real accelerator, and unfortunately this is pixelated, but I hope you see it. In red we have both results for simulation and experimental results for the reinforcement learning algorithm. What we are seeing here, it's just an error, so the lower the error, the better it performed. So you can see that reinforcement learning does outperform Bayesian optimization, both in simulation and experimental deployment for a tuning task. And then we just compared it for reference with extremum seeking, Nelder-Mid simplex, and just absolutely random search, which is always nice to see in comparison. So we did have some success with reinforcement learning as an optimizer. It costs to train quite a bit. And here's how it reacts in the actual accelerator. So you can see that the reinforcement learning algorithm, we have here the actions, and here are the observations, so the mean on the screen and the size on the screen. And you can see that the reinforcement learning optimizer converges quite fast to the actual solution that it likes. Whereas Bayesian optimization is, of course, building its model online, which is, of course, a little bit unfair because we pre-trained the reinforcement learning-based optimizer. So it's much more noisy. But they achieve very similar results. So it really depends on the amount of work one wants to do before that. We also did a little comparison on manual tuning versus the reinforcement learning optimizer, and we could cut some time in that tuning, which was also great to see. So that's just to show you that we can also a little bit abuse reinforcement learning to just use it as a pure optimizer and have nothing to do with control. And now I will talk a little bit about reinforcement learning, which I think is really cool. So it's going to be, does any of you do reinforcement learning at all? Okay, cool. Then it's new for you. That's good. So you might be familiar with neural networks and supervised learning. So you have regression and you have clustering, and that's what it's used everywhere. I'm pretty sure you're familiar with that. But reinforcement learning is one of the other learning paradigms. With, as I mentioned, real-time decisions, gaming, self-driving cars, robotics. And here I just wanted to highlight that for every learning paradigm, there's a deep learning version and not deep learning version of that. Reinforcement learning is quite new. Now I will tell you a little bit about the history of it. But right now, modern reinforcement learning is basically mainly deep reinforcement learning. So what's cool about reinforcement learning is that it's, I would say, a little bit more than just machine learning, because it drinks from behavior learning. It has inherited concepts from psychology, like the classical conditioning. That's why it's called reinforcement learning. It also borrows the reward system from neuroscience, uses game theory from economics, operations research from mathematics, and optimal control and planning from engineering. So it's a very cool paradigm. And just to show that it's becoming, like, it's on people's minds, the Andrew Barto and Richard Sutton, which are the authors of the main reinforcement learning book or manual that we used to learn. They recently received the Turing Award for their work in reinforcement learning. So just to say, there's active work going on into it. And what we know today as reinforcement learning was established in the 80s. So it's actually quite new. So on the one hand, it takes trial and error learning, and it takes the behavioral basis of that. So the fact that learning emerges through repeated interaction with an environment, like the humans do. We have a reward feedback and some sort of adaptation. Then it also uses optimal control. That's a mathematical framework. So it uses Markov decision processes as the main modeling tool, the Markov property, Bellman equations, Markov property, that's only for ideal cases. Then we go to partially observable MTPs, value functions, policy functions, and dynamic programming. And then it also uses, that's the last piece of the puzzle that makes reinforcement learning extremely efficient, which is temporal difference learning, and that provides us the adaptability and scalability that makes these algorithms actually usable. It enables prediction and learning from partial experiences. So what we do is a linear approximation. Instead of we just bootstrap our values for the next steps. It's just an approximation that makes this actually doable. So what can reinforcement learning do in practice? Deep reinforcement learning, where we approximate certain functions with neural networks, they manage to, well, you might know the Atari games. One of the first applications of deep reinforcement learning was basically gaming making an agent play the Atari games, and you can see that it found the best strategy, which is just basically make a small hole and remove all of those blocks. So it works extremely good in simulations. Also, we have bipeds that learn from scratch how to walk in a physics environment. So this is how it looks like when it has learned through different episodes to interact with the environment with no previous training. And it's very nice to see that a biped with these characteristics walks sort of like us. I guess it makes sense. In science, it has been used for the control of fusion reactors, tokamaks, and we have a lot of gaming involved, so it's very nice. I wanted to go a little bit into how reinforcement learning works, even if we don't have much time. But this is the classic reinforcement learning loop that you will see in every book or paper. You have an agent. Is the anthropomorphization of the actual algorithm, but we do call it an agent, that can interact with the environment through actions. So we do select the actions that we want. The environment, it's usually partially observable. So it's fully observable, like in the Atari game. If it has access to all of the pixels, then that's fully observable. But if you are acting in real life, it's never going to have all of the information. So there's partial observability. The agent can observe the environment through a certain amount of states, which is the ones that we can give it. And the goal of the agent is to collect rewards. It's a very simple thing, but it just wants to collect the maximum amount of rewards that we, the engineers, set for that. And this is where the trial and error inheritance comes from. This is learning through trial and error. We try an action, we observe how much reward do we get. If we don't like it, we change our action. Yes, so basically this is encoding a little bit free will, perception, and motivation within your agent or algorithm. The reward is just a scalar signal, so it's just a number, and you need to encode in that number whatever you think is relevant from your system, so that's actually quite difficult to do. And we define this cumulative return, which is just the sum of rewards that you get over time. So how many you have, and we just like weight it so that the first rewards, present rewards are more valuable than very future long-term rewards, but it's a parameter that you can tune. The goal is the maximization of this cumulative reward, so we want as much of it as possible, which the agents exploit actually in a lot of situations. So if you don't set it properly, it will exploit it in a way that you didn't want to. And what's interesting about this is that there's this paper by David Silver called "Reward is Enough," which states that this very simple goal maximization is enough for the emergence of intelligence behavior, which is true because intelligence, if you consider this intelligent behavior, then yes. But there's many people that don't consider that intelligent behavior. So there's, of course, someone else that said scalar reward is not enough. So I invite you to just read those papers and make up your mind for yourself. And this is all modeled with Markov decision processes, which is this tuple of state space, action space, transition probabilities, reward functions, and this discount factor, which we don't need for this talk, but just to let you know. But how does it learn? Because if we're here, we take an action, we observe, there's no learning mechanism here. It's learning in nature through trial and error is it's not going to be very efficient. So it does have two learning mechanisms inside. So the first question is, what behaviors perform well right now in this environment? And this is the policy, which is just a map between state and action, meaning if I am in this state, I'm always going to take this action. And we denote it by pi. If it's deterministic, every time we're in this state, we're going to take this action, but it can also be stochastic where we have a probability. So it's like when we are in this state, there's a probability that we take this action. So it's the agent's behavior function. And we have another way of learning, which is to estimate the utility of taking actions in particular states of the environment. So say if you have a fixed policy right now, and I want to know, how is this policy good? Should I change policy? What is the value of behaving in this way in this whole environment? Then we have the value function. It just tells you how good your policy is. It attaches a value, a number, to what you are doing right now, to your behavior in this particular environment, which, if you're interested, it's just the mean of your reward distribution. So we're trying to maximize our rewards with this. So you can do two things with reinforcement learning. You can do predictions. So in this case, you want to evaluate the future given a policy. So you have a fixed policy. We're going to see how valuable this is, and that's what we're going to do. Or we can do control, which is when we iterate over policies, meaning we're going to learn by learning new behaviors that are optimal for us. So I don't get I'm not going to get into too many details, but the policy function and the value function in deep reinforcement learning are neural networks. So they are functions that can be absolutely completely represented by deep neural networks. And of course, then what we do is we tune the hyperparameters with gradient descent. And this is very nice, and it allows us to have all of these multidimensional problems like in video games and so on. And we can process images very fast, which is extremely great. But there are problems with generalization capabilities. We need a lot of good data. So quantity and quality of data, they really matter. In deep reinforcement learning, we're doing a lot of approximations, so there's no convergence guarantees. Now we are living the land of theoretical guarantees. That is not guaranteed anymore. And there's a lot of training stability due to the accumulation of approximations that we are doing. So there's, I put together a little bit of the challenges that we are seeing in accelerators while using reinforcement learning. I'm going to talk only about some of them today because we unfortunately don't have time today. But we have sample efficiency, partial observability, and safety. And we can do simulation-based training, we can do experiment-based training, and we can do a hybrid of those. So I'm just going to show you a little overview of that. So sample efficiency basically is the number of interactions that with the environment required to achieve a certain level of performance during the decision-making process. Basically, if our sample efficiency is high or training cost is down, which is what we want to do. And we wish that we said, okay, we always use this algorithm and then we're done. But we don't know, because each algorithm has its pros and its cons, and it really depends on the problem that you're applying it to. So unfortunately, I cannot tell you use this or use that. For example, one of the PPO agents, they're extremely simple and it's very popular because it's very easily deployable and doesn't need too much tuning, but it's extremely sample inefficient. Then we can also do models free of policy, actor critic, which are extremely powerful. They're sample efficient, perfect for continuous action, and they're stable, but they're very hard to tune. So if you're not really into this and you don't want to waste time doing this fine tuning, then this is not going to work for you. So there's not a single answer of what algorithm you should use. We wish we knew, but we don't. And I want to talk about simulation-based training for us in accelerators. When we want to train reinforcement learning algorithms, we were going to need to interact with a simulation. So the simulation is going to be our environment, but we need at least from 1,000 to 1 million interactions, depends on what we're doing. And if that simulation is not tractable, we're not going to be able to do it. So we suddenly start to need faster versions of the simulations that we're using, and we need to be able to create enough varied data for that. Then many times we pre-train a simulation, we pre-train a policy, and then we want to validate it in the actual accelerator. This creates, of course, the tension between an idealized setting and a noisy and predictable dynamics. So this is what we call the sim to real gap. And that's why we need robust policies. So what we do is we use techniques like domain randomization, which means that instead of training in one particular environment, we train in variations of that environment. So instead of training in one environment, we do a distribution and we train on the mean of that. And that creates enough variety so that when we deploy it in the real accelerator, we can absorb the unpredictability of the noise. And we also have meta reinforcement learning, which is very cool, where we can, it's like learning to learn. And you learn different tasks, so you learn in different distributions of tasks. And then you just fine tune it when you deploy it. And it's also extremely powerful, but more costly engineering-wise. So I wanted to show you one of the examples that we used in a simulation of an accelerator. There's the awake beam dynatron, where we use not many actuators, 20 actuators and 10 observations. Doesn't matter, we were trying to tune the trajectory across an accelerator, and we tried different methods of training. This is the number of returns, so the rewards. So the more rewards, the better, let's say. So when we classically train, we start quite low in terms of rewards, and then it does pick up eventually. When we train in the mean of this distribution that I told you, then it's a little bit better. And when we train in different distributions of tasks, when it's sort of like learns like us, like we learn to do different things in different environments, and then we just put it together and are able to adapt to another thing, then we start with very nice rewards from the very beginning. So this is very promising for immediate, like what we call zero-shot or few-shot optimization. Now I'm showing you another part of the reinforcement learning based optimizer compared to the Bayesian optimization optimizer. We're talking about tuning, and we're talking about what do we need to assume when we tune, which is that the environment is not changing, and when we reset between tasks, we are sort of having the same environment between accelerator shots, beam times. What we did here is we induced a failure, so we changed the let's say the strength of one of the magnets that were focusing the beam in the previous example that I showed. And what we saw with the reinforcement learning based optimizer, it was that it was robust enough to absorb the change and to correct it immediately. Whereas for the Bayesian optimization model, well, the surrogate model that we're building with the previous samples was not good for that environment anymore, so we can see the oscillations that and the limitations of that particular thing. Of course, this was supposed to be a tuning task, so you should not be using Bayesian optimization thinking that it's going to be able to absorb things like very rapid changes or failures. But this was a nice way to compare both. And we have now the very rare situation of training a reinforcement learning agent directly into the experiment, so directly into the accelerator, meaning no pre-training was done before. We only have a handful of cases, and it only works when certain conditions are met. What is nice is that no more than 1,000 real-world interactions were required, which is actually extremely impressive, meaning if you design your algorithm correctly and you deploy it in the real machine, with 1,000 interactions, you might be able to learn the thing that you wanted to learn without previous training, which I think is really great. But there's a trick. Of course, here we have low-dimensional action and observation spaces. We had a dense reward. What a dense reward means is that we're having observations where we can compute the reward very often. Like, for example, if you're playing a game of chess, that is one of the sparsest rewards you can get because the win, if you win or you lose, you only know it at the end of the game. Still, reinforcement learning very good for this because we can do credit assignment within the trajectories before you know your reward. But here we need really dense rewards for this to work. And it's also very sensitive to hyperparameter choices. So there's a lot of tuning to do in the control room. It's hard to find dedicated beam time. And there's, of course, safety concerns because hard safety is not guaranteed with reinforcement learning. So you need to work in accelerators, like, for example, electron beam lines or something where if you lose the beam, you're not going to damage the actual machine. We did one of these instances of training online without previous training. We tried to use it for control. So I see that I have 5 minutes left, so I'm going to try to bring it all together. So we were trying to be very ambitious and to try to control an instability. There's a longitudinal instability that develops in certain accelerators where we're trying to compress the long longitudinally in order to get coherent radiation. And this creates, we like the light, we like the properties of the light very much, but they come in bursts, and this is not great. We would like it to be more constant. So we were trying to control this without whole hardware setup, custom made, which we don't have time to get into today. But we did have a reinforcement learning policy that was running in fast inference in a Xilinx board, and then we were training it after certain episodes in the control room computer. So how did this look like? We just took the raw signal of what we were observing and we just decimated it a little bit. Our observation went to action directly. I'm not going to get into the details. I'm just going to show you the results. You can see here the signal that we're trying to control. We're trying to make it less spiky. Episode 0, of course, it looks the same. We have in red what the RL agent does and the gray with the feedback off. And we can see here that in episode 29 is sort of learning. So you can see that without the agent, it would be spiky. And with red, we're getting a more constant, less variance sort of emission. And we see that when our instability is not working anymore, the agent is trying to actually activate it and kick it. And we can see in terms of rewards, a little difference between reinforcement learning and feedback off. So this was a very complex experiment to set up, and we believe that the algorithm needs to be much more complex and probably model-based because the dynamics here were changing very quickly, and not even reinforcement learning can adapt to such fast changing conditions without a model, actually. But we did try it in a much simpler case, so same thing, same setup, but for another thing. We have a beam. The beam has natural oscillations transversely, and what we did was, these are the natural oscillations, and we kicked it with one of the magnets, and you can see that the natural decay is the blue one. And we made this agent to learn how to dump it as fast as possible. So after around 60 episodes, you can see that it dumps it quite well, and we compared it to the actual commercial solution, which uses a finite impulse response filter. And we saw that it has the same sort of performance as the commercial solution, which was really great to see this algorithm learn just by interacting with the machine and saying nothing else. And this worked because these episodes are very reproducible. So once it learned about how it worked, it could very efficiently apply the best policy, whereas with the instability, it was changing so fast that it was much more difficult to do. So for reinforcement learning, you have seen already that it's for sequences of actions, temporal, causal, structural, delayed objectives, real-time, non-stationary, or history-dependent problems. For the summary and outlook, we have seen that tuning and control are distinct problem classes, different timescales, information structures, and constraints. That Bayesian optimization is very nice for static tuning problems and expensive evaluations. That reinforcement learning is appropriate when sequential structure matters. And that we can also use reinforcement learning to learn fast and robust optimizers, amortizing the cost of interaction with actual engineering effort. And that classical control remains essential when models are operationally usable and guarantees dominate. And the outlook, I think we should be looking at hybrid formulations. So we're looking a lot into model-based control, like GPMPC, model predictive control, and we can have actually different algorithms at different levels of the pipeline. We don't need to just commit to one. We can combine the first principle models and simulations with learning-based components when the models are accurate but not deployable online. And I would say this abstraction choice between static optimization, learned optimized, or sequential control, it should be more adaptive and not like fixed, like we only do one, and we can change across operational regimes and timescales. I think we need safer and more efficient learning, like reducing the cost of exploration in online reinforcement learning. Otherwise, we're not going to be able to actually deploy it in accelerators. Incorporating anything that we know beforehand, like constraints, priors, operator knowledge, more systematically will always help. And to bridge the gap between this practical deployment and these theoretical guarantees, which we actually don't have right now. And then this is more maybe sociological, but we should probably have clear decision rules for tuning versus control versus learn optimization in our accelerator tasks. Avoiding method-driven choices in favor of problem-driven modeling, and this shared language between control optimization and learning communities, because we are using different languages for different things. So that would just be nice to see. And if you're interested in reinforcement learning, we're actually having a workshop on reinforcement learning here in Liverpool in Easter. So we're closing registrations this week. So if you're around, and it's very nice for beginners too, please join. Some references for you, and that's all for me. Thank you.
Okay, so I'm gonna go to the room first if anyone has any questions, and then I'll move online. And then in the chat as well, ask questions in the chat or put your hand up and I'll ask you to read out loud. Okay, so in the room, is there any questions? Sorry, that's fine because there's a few online.
It was a lot.
Okay, we start. I'll start in the middle. So, have you tried any Gen AI algorithms for Bayesian analyses? So, anywhere or suitable prior or conditional probability, like GAN, VAE, etc.
I have not. I have personally not. In terms of priors, there's a whole group. There's a whole team of people in Slack that have worked on using disinformed priors. So instead of having a prior with no information, we just whatever we have, we just include that information beforehand, and it really improves efficiency. Yeah.
Thank you. Another question is what I think this is how they're phrasing it. So, what's your view on? I think it's agentic AI. So that's meant to replace managerial tasks, and it's the next step for Gen AI.
Yes, I'm not really into that. I'm really just into tuning and control. There's they mean now with also LLMs.
They didn't say it, but I mean,
and foundation models. Yes.
Yeah.
So there's some work now where we're trying to. Well, first of all, there's logbook analysis with large language models. So there's a whole thing like having all of these logbooks. So you can just talk to a chat that has been trained on the logbooks and ask about it. But there's another way where you could say, for example, for the tuning test that I showed before, technically, if you have this foundation model, you could say, please tune my beam, like in natural language, like please tune my beam to this position and this size. and then that would be connected to whatever, I guess, optimizer you would have. So I guess I don't know if that's what they mean with agentic, but the people at DESI have a little bit of work on that, and actually many other facilities are trying to.
Yes, still, thank you for the answer. I think that answered it. Okay, a few more. Okay, so for a medical accelerator that is already commissioned, what are the risks and challenges when trying to implement reinforcement learning?
I wouldn't know. So, unfortunately, reinforcement learning does not have hard safety because exploration is part of how it learns. There's a, depending on the algorithm you have, there's a balance between exploration and exploitation. One could pre-train in simulation, have all of the exploration either without a patient or whatever, and then focus only in exploitation. So I would have it as a reinforcement learning based optimizer, as we showed here. It means you train in whatever, can be real life, can be simulation, but then you fix it and you just run fast inference. And the most important part is that the safety constraints are going to be there no matter what the agent does. So basically, the limits of what you can do with the beam, with the agent, they need to be externally implemented. Otherwise, I wouldn't recommend it.
Nice, thank you. Okay, I'll take the last 3 questions from the chat, and then if anyone has any more questions, please put your hand up, or put them in the chat within the next minute. So, whilst this was briefly mentioned, for Bayesian optimization, is there an acquisition function that you found that performed better? And then part 2 of that is, what is the decision process in choosing such a function?
It's so problem dependent. So I did skip actually through the acquisition function because I didn't have time. I think the most commonly used is UCB, so upper confidence bound, and EI, so expected improvement. And I mean, it's very simple. Like if here we're using UCB and you're just going to sample the region with more uncertainty, which is very logical. So one would need to look at your system and see if that's what you want. But I think we'll converge between EI and UCB would be one of those.
Thank you. Okay. I will. Okay, I'll take 2 more. I'll take one question that's been asked already, and I'll take this last question, and then I think we'll call it quits there. So, are you aware of any ways to build physics-informed optimizers to improve the sample efficiency?
Yes. Rather than physics-informed, because when I think of physics-informed, I'm thinking about these neural networks that have all of these biases inside. I'm thinking more about model-based. We are going towards model-based, meaning that we have a model can be a Gaussian processes. Actually, you can take a Gaussian processes model and don't use Bayesian optimization for it. You can use model predictive control. So I think that it's the key, like where we have to go into that direction, because that's going to really help predictions. And you can do predictions with them, and you can have uncertainty quantification of that, and that's exactly what we need for accelerator. So yes, anything physics informed or using a surrogate model, I think that's where we need to go.
Okay, perfect. And then last one, I hope it's an easy one. So on slide 13, the question is, don't we have Bayesian ways for dynamic systems?
I don't. Can we clarify what?
Yeah, so this is the question. Pritam, this is one of your questions. If you want to speak up to clarify.
So one can include time as one of the parameters, but that is sort of cheating. No, it's not cheating, but yes, we can fit time. So if we have all of the parameters of our system, and we can fit time as a contextual parameter, but that does not mean that Bayesian optimization is used for the proper dynamical processes. It's not the same.
Thank you. Okay, I will call it there. Everyone online is saying thank you for all of the responses.
Thank you, guys.
Can we say thanks again? Okay. Thanks again. Do you want to do an announcement about the next one, or I'll pass it over to you for housekeeping?
Okay, so the next data science seminar is in 4 weeks' time, so that'll be Tuesday, the 10th of February. I say again 3 o'clock on a Tuesday afternoon. So I say hopefully we will see you all there. Thank you.